Hello everyone, welcome to my new video on my Mathematics Essentials series. The topic of this video sounds a bit like the title of a novel, The Ambiguous Case of the Sine Rule, and this is something I've alluded to in previous videos. And it's to do with the fact that even though the sine rule is often quicker to apply in practice than the cosine rule, you have to be careful using the sine rule when your triangle contains an obtuse angle. And an obtuse angle is just an angle that's greater than 90 degrees or greater than pi over 2 radians. Okay, what's responsible for this ambiguity? Well, it's this trigonometric identity here, that for any angle between 0 and pi radians, strictly between them, the sine of that angle is always equal to the sine of pi minus that angle. Okay, so the sine of theta is equal to the sine of pi minus theta. And to see why this is the case, well, if you just consider a unit circle, okay, so I'll draw a coordinate axis, and I'll try to draw a unit circle that's neat enough for our purposes. Okay, so this isn't a very neat unit circle, but okay, for any point on the circumference of the unit circle in the, let's say the positive quadrant, so considered as a cast diagram, okay, we have C, A, S, T. So we can see that sine is positive in two quadrants, this quadrant and that quadrant. Okay, now this point on the circumference of the unit circle, I'll just call it P. Okay, it has components, an x component and a y component, which I'll just label with x and y. Okay, and you can see that if we track across, if we were to imagine a horizontal line, okay, it's going to hit the unit circle at some other point. Okay, I'll call that point Q. All right, and it's going to have the same y component. All right, so these two points, all right, define a line segment between them and the origin, okay, and each of them defines an angle. So we have this angle, okay, and we'll call that angle theta, and we also have this angle here, all right, and given that the sine of these angles are just the y components of these points, okay, Q here has the component negative whatever x is, but the same y component as the point P. Okay, sine of both angles is equal. All right, so this green angle, all right, I'm just going to call phi. Right, and you can see that this angle here is also theta. All right, and to convince yourself of this, if you just imagine the right angle triangles defined as so. Okay, we have these right angle triangles, and they're symmetrical because their hypotenuse are the same. Right? Why are their hypotenuse the same? Well, the hypotenuse is just the length between the point on the unit circle and the origin, or the distance, more precisely. Okay, so they have the same hypotenuse, and those hypotenuses are of length 1. All right, they have the same y component, which means the vertical side of each triangle is the same. Its length is whatever y is. Okay, and the horizontal lengths of these triangles, well, even though the point Q has the x component negative x, and the point P has an x component of just x, okay, as lengths, they are the same because lengths are always positive. You can't really have a negative length. So both of these triangles have the same length of their base sides. All sides are of equal length. These triangles are symmetrical. All right, so this angle here is also theta, which means that the angle that I've indicated in green and denoted by phi, all right, well, how would we get to that angle? That would be just like going pi radians around the unit circle and then going back by theta many radians. Okay, so in other words, phi must be equal to pi minus theta. Okay, now theta is an acute angle, which is to say that it's less than pi over 2 radians or less than 90 degrees. Right? So here we see that taking the sine of some acute angle is also equal to taking the sine of some obtuse angle, because when you have pi radians, well, that's just, you know, 2 right angles worth of radians, right? And you subtract something that's less than a right angle, you're still left with something that's greater than a right angle. Okay, so that's why the identity is true, or geometrically why it is true. I'll probably in some upcoming video prove that identity without, well, I mean, resorting to geometric diagrams is not a proof, so, you know, I'll prove it algebraically in an upcoming video, probably. But let's take a look at how the ambiguity actually arises without looking at a unit circle. Let's consider two triangles in which the angle that we are looking for is kind of underdetermined, okay? It's not clear whether we are looking for the acute angle or the obtuse angle. Let's consider a triangle like this one, actually this. So it's not a right angle triangle, okay? And let's say that we are given this angle here, all right? And this angle, let's just work in degrees. Okay, that angle is 40 degrees. And we are also given this angle, which is, let's say, 5 centimeters, or pick whatever units you want. All right, and this one here is 4. Okay, now let's label these angles and side lengths. So let's say that this is A, all right, which would mean that this is the side A. Okay, and this angle here is B, which we know is 40 degrees. All right, and that would make this side lowercase b. Okay, which means that this angle would be C, and this side length would be lowercase c. Now I want you to consider the following. Consider this side, okay, the side B, and imagine that we can swing it down because it's on like a hinge, okay? Imagine there's like a hinge at this point, at this vertice C, okay? And as we swing it down, okay, it detaches from this point up here, all right? And I'm just going to sort of indicate a few sort of time stamps of what's happening as we're letting this side length collapse a little bit. Okay, it's going to protrude from C, the side C, so it's going to intersect it. Okay, and as it swings down past a certain distance, it's going to protrude less and less and less until eventually it just lines up well. Okay, it just precisely, okay, reaches the side C. All right, now what we have is another triangle, right, which actually has the same parameters as our initial triangle. Okay, we've got this smaller triangle inside another triangle, and it has all of the same parameters that we were given in some problem. And in this problem, we're asked to find A. So, find A. All right. Well, I'm just going to draw this triangle down here. Okay. Looks something like this. All right. And we have the angle B. Okay, that's still 40 degrees. Okay, and from our diagram, okay, all we did was we swung the side B down until it defined a new triangle. So these two sides have the same length, right? Which means this triangle, the smaller one inside the initial triangle, satisfies all of those same parameters. Okay, we have a side of length 4, right? We have a side of length 5, right? We still have that angle B of 40 degrees, but now, whilst we have C, and C is different, okay, we have another A. Okay, we were never given C, all right? And we were never given A. Okay, so this new triangle and our initial triangle, both of them satisfy the parameters, which means if you were to use the sine rule and then, for instance, use a scientific calculator to find out what the angle A is, okay, your calculator doesn't actually know whether you're looking for this A or this A. So just to draw this diagram again, to make another point, obviously, I'm not just drawing it again for the sake of it, okay? So just imagine that this is the initial triangle we drew, okay? And this here is the other triangle we defined inside the larger triangle, all right? There are really two candidates for A, and each of them are like competing for the right to be the A, but there is not really any one of them that deserves to be the solution to your problem any more than the other, okay? Unless you somehow initially know that the angle that you are looking for is an obtuse angle, okay? So if the A you are looking for is this one, then you know you're looking for an obtuse angle. If, on the other hand, it's this one, then you would know that you are looking for an acute angle. And to have a unique solution, in other words, to not have to provide two distinct answers, one an acute angle and one an obtuse angle, as your solution for the value of A, you would need some extra information to determine that you're actually looking for an obtuse angle or you're actually looking for an acute angle. You need to know ahead of time which kind of angle you are looking for. So let's just do a quick example with the values that are given. So we know that B equals 4, A equals 5, and the angle B equals 40 degrees. Well, consider the sine rule. And I'll just write out what we're asked to find. Find A. Okay. Well, we would have the sine of A over the side length A, which is 5, equal to the sine of B, sine of the angle B, but B is 40 degrees. Okay, so we know what this is now. Okay, it doesn't matter that we can't write it as some number. This is really some number, okay? So we can treat this as something we know over the side B, all right? But B is 4, okay? So then to isolate A, we would start by multiplying both sides by 5, and we would have sine of A equals 5 times the sine of 40 degrees over 4. Then to isolate A, we would take the arc sine of both sides, which on the left-hand side just gives us A, and on the right-hand side, we have the arc sine of 5 times the sine of the angle 40 degrees divided by 4. Okay, now, if you punch this into a scientific calculator, maybe they have some really good ones nowadays where they return both solutions, but in my experience, they will only return the smaller angle. They will return the acute angle. Okay, so if I punch this into a scientific calculator, just give me a second. Okay, we're going to have the arc sine of 5 times the sine of 40 degrees over 4. Okay, A is approximately equal to 53.46 degrees. Okay, and that's what you would call the principal angle, all right? But if you knew that the angle A was an obtuse angle, then in order to find A, what you really want is this. A equals 180. Now, it might be tempting to subtract 53.46, okay, but that's just an approximation for the angle theta, okay? And right now, we're taking pi minus the angle theta, or because we're working in degrees, 180 degrees minus theta, all right? It turns out that this is really our theta if we knew that we were looking for an obtuse angle, okay? If we don't know, all right, then both of these are solutions for A, and there's no reason to exclude one of them, okay? So given that this is an approximation, it might be equal to find the other value for A by writing something like this. But because you have an equal sign here, not an approximately equal sign, you shouldn't do that because your answer would be an approximation. Instead, you should subtract this here. Okay, so to find A, it would be 180 minus the arc sine of 5 times the sine of the angle 40 degrees divided by 4. And that way, when you approximate, if you punch this into a scientific calculator, your approximation doesn't lose any more accuracy than it has to. So punching this into a scientific calculator would yield approximately 126.54 degrees. Okay, so both of these solutions, okay, you would have to write something like this. A is approximately equal to 53.46 degrees, comma, 126.54 degrees. Okay, and if you wanted to leave your answers in exact form, you would write that, comma, that. Okay, so this is an example of the ambiguous case, and what is the ambiguous case precisely? It's when you are given two side lengths and an angle. So I'll write this down for you. Okay, ambiguous case. of the sine rule. Ambiguous case. Okay, you're given, if you can hear that, if you can hear a laughing sound, well, I live in Australia and it's early in the morning. It's about 6:25 a.m. And we have this this bird that's native to Australia called the kookaburra. You might want to Google search a kookaburra if you haven't heard of them. But yeah, they make this laughing sound that kind of sounds like a monkey. So if you're wondering what that is, it's a kookaburra. Okay, they're pretty friendly. You can kind of tame them and walk up to them and feed them in the wild if they're used to your company. Anyways, back to the ambiguous case of the sine rule. Okay, given two sides and an angle opposite one of the sides. Okay, an angle opposite one of the sides. Opposite one of the sides, you know. Okay, right. And you are asked to find an angle opposite, again, one of the sides, you know. Opposite one of the sides. You know, that's the ambiguous case. Okay. If instead you were given two sides and an angle between them and asked to find, for instance, a side, okay, don't get confused and think that that's the ambiguous case, okay? And the cosine rule is really suited for that kind of case. So anyways, I hope this helps you understand the ambiguous case of the sine rule and how not to get tricked up with it when applying the sine rule, especially when you're using a scientific calculator. If you enjoyed this video, give it a like, feel free to share it. If you have any questions, just post them in the comments. And if you would like a notification when I upload a video, just subscribe to my channel. Until next time, bye for now.